All right, today we're going to decode a secret language. Seriously, it's a language that uses simple algebra to map out the lines, the shapes, the very patterns of our world. It's called coordinate geometry, and it all kicks off with one pretty mind-bending question.
I mean, think about it. How can one short string of letters and numbers possibly hold the blueprint for a line that goes on forever? Well, it's not magic, it's just a code. And over the next few minutes, we're going to crack that code together.
So, check this out. Every single straight line you can possibly imagine has its own unique secret code. And once you learn how to read it, you know everything about that line. Its direction, how steep it is, every single point it's ever going to touch. And the best part? The code is surprisingly simple.
And here it is. This is the master key to the whole thing. Y equals mx plus c. So m is what we call the gradient. Just think of it as the line's steepness. Is it a gentle slope or a steep cliff? And c? That's the y-intercept. It's simply the exact spot where the line crosses that vertical y-axis. You understand m and c, you understand the line. Period.
But here's the catch. Life isn't always that neat. Equations don't always come gift-wrapped in that perfect format. So, our first tool in the toolkit is all about rearranging things. No matter what the equation looks like when you first see it, your mission is always the same. Get y all by itself on one side of that equal sign.
All right, let's do one. We've got 3y plus 2x equals 5. First things first, we got to move that x term over to the other side. So we subtract 2x from both sides. That leaves us with 3y equals negative 2x plus 5. We're so close. To get y totally alone, we just have to divide everything, and I mean everything, by 3. And that gives us
y equals negative 2/3 x plus 5/3. And boom, just like that, it's in our standard y equals mx plus c form. The number that's glued to the x, that's our gradient. So for this line, the gradient m is negative 2/3. Simple as that.
Okay, so now we can find the line's gradient. Let's dig into its relationship with the points that actually live on it. This brings us to our second tool, and it's based on a fundamental, unbreakable truth of geometry.
Now, what does satisfy the equation even mean? It's really simple. It just means that if you plug a point's coordinates, its x and y values, into the line's equation, the math just works. The left side will equal the right side. It's like the point has the right password to get on the line. It's a universal rule.
So let's put this rule into action. We're told that the line 3y equals 2 minus x passes right through the point 5, k. So we know the x value is 5, but the y value is a mystery. Our mission is to use our point of truth rule to figure out the value of k.
Okay, so we just substitute what we know right into the equation. Wherever there's a y, we put in k. Wherever there's an x, we put in 5. The equation now becomes 3 times k equals 2 minus 5. We can simplify that right side, which gives us 3k equals negative 3. And now for the final move, we just divide both sides by 3. And there it is. The value of k has to be negative 1 for that point to be on that line. See how that works? It's a super useful trick.
So far, we've been looking at lines one at a time. But lines don't exist in a vacuum, right? They interact. They can run parallel to each other forever, never touching, or they can cross. Our third tool deals with a very special kind of crossing, when two lines meet at a perfect 90-degree angle. This is the perpendicular principle.
And the rules for this are really elegant. For two lines to be parallel, it's easy. Their gradients have to be exactly the same. That's it. For two lines to be perpendicular, though, they have a special relationship. When you multiply their gradients together, the answer is always negative 1. Okay, let's apply this. Remember that very first line we worked with? We figured out its gradient, let's call it m1, was negative 2/3. So the question is, what would the gradient be for any line that's perfectly perpendicular to it?
Well, we just apply our new rule. We know our first gradient, negative 2/3 multiplied by the new perpendicular gradient, m2, must equal negative 1. So now we just have to solve for m2.
And when you solve for m2, you find it equals positive 3/2. This is called the negative reciprocal. You literally just flip the fraction and change the sign. So 2/3 becomes 3/2, and negative becomes positive. That's the secret handshake between perpendicular lines. All right, it is time to bring everything together. We've learned how to find a gradient, how to test a point, and how lines relate to each other. Now, let's use all of those tools to solve one final puzzle. Here's our final challenge. We've got 2 points, B and C.
We have the full coordinates for b, but only half for c. We have this unknown p. But here's the twist. This time, we aren't trying to find the gradient. We're given the gradient. It's -3/4. Our job is to work backwards and find that missing coordinate, p.
To solve this, we've got to go back to the basic definition of a gradient. Remember, the gradient m is just the change in the vertical direction, the rise, divided by the change in the horizontal direction, the run. The formula for that is y2 minus y1, all divided by x2 minus x1. Let's just plug in the numbers we know.
So let's substitute everything. Our gradient m is -3/4, the change in y is -1 minus 5, and the change in x is our mystery p minus 1. And just like that, we have an equation with only one unknown.
Now, when you have an equation that's a fraction equal to another fraction, the fastest way to solve it is this cool trick called cross multiplication. It gets rid of the fractions instantly. You multiply the top left by the bottom right and the bottom left by the top right. This gives us a much cleaner equation to solve. -3 times the quantity p minus 1 equals 4 times -6. From here, we're on the home stretch. We just solve for p. Distribute the -3 on the left, multiply the 4 and -6 on the right. A couple of quick moves later, and we get our answer. P equals 9. We found the missing piece of the puzzle.
So we've seen how these different tools, rearranging equations, substituting points, using the gradient rules, all come together to form this powerful toolkit. But honestly, this is just scratching the surface. This same logic can describe circles, parabolas, entire complex systems. So the real question is, now that you have the toolkit, what are you going to choose to unlock next?